So I'm Victor. I work for RISC. I work on the platform, the cryptography, and also some Web3 integration work. And my talk I'll talk about is titled Pretty Optimal, Integrating ZK Circuits and zkVMs and Circuits. And I'll explain why it's called that in a second. So one thing I want to start with just right off the bat is a kind of some context setting, which is that we are living in a world where zkVMs are practical for a wide range of applications today. So right now for Zero, for instance, and there are others as well, basically you can compute about 1 million RISC-V cycles in 5 seconds on a GPU, or about 14 seconds on a Mac M2 Pro. 1 million cycles is plenty of time to do things like JSON parsing, signature verification, chessboard, checkmate validation. There's a lot of things you can do in a million cycles. And we also support continuations to go to billions, tens of billions, even 50 billion cycles or more. That's the largest we've done so far, but there's nothing that's stopping us from going further. One thing I want to call out in particular as well is people think that recursion is expensive. And it's not exactly cheap, but it's much less expensive than you might think. Right now we can do a 2-to-1 recursion, verify 2 proofs, produce 1 proof, in about 1 to 2 seconds on a GPU and 3 to 4 seconds on a Mac M2 Pro. So when you think about recursion, don't think it's actually not as expensive as you might think. Also programmability. Basically, you can actually compile programs using standard tool chains, Clang and RISC, and actually run those binaries in zkVM. And I do want to mention the limitations, which is that so RISC-V instruction set is not the most efficient representation for cryptography operations. So things like ECDSA verification, things like pairings, et cetera, do take a significant amount of cycles. However, often not as many as you might think. Oh, and one other thing as well. Proving on mobile phones and browsers is possible. It's not a seamless UX, and we'll talk about that more later. So the question with that context set I want to ask is, when should we write circuits, and when should we write programs? By programs, I mean programs that run in a zkVM. So programs are generally more efficient with your engineering time. It's faster to implement them, which is a significant cost savings. And if you're a startup or a protocol, or really anybody trying to get your application out to the market, this matters a lot. It's simple for human review. This includes security review, meaning less bugs. There's often less code involved because you have to maintain libraries that are maintained by other teams. And that results in lower maintenance costs, and also, again, less bugs, which is incredibly important when we talk about soundness of zero-knowledge proofs. Circuits really maximize that computational efficiency. So if you're trying to really crank it and get maximum throughput or minimum latency, circuits are basically the best environment for that in many cases. There are, basically, in particular, there's kind of this distinction between throughput and latency, where basically latency, by that I mean the minimum time to produce a proof end to end, and by throughput I mean how big of a proof can you do? If you're trying to prove an entire blockchain, that's throughput. If you're trying to do a 200 millisecond proof on a mobile phone, that's latency in my mind when I refer to those terms. And one thing I want to make very clear about here, and this is why I call it pretty optimal, is that optimal really needs to concern more than just performance. It's not just about how fast can the program run, it's about how easy is it to write, how easy is it to maintain, are there any security bugs, basically what's the user experience, what's the developer experience like. These are all very important things when you're talking about actually shipping an application that's going to produce real value for real people. Now, I'm a software engineer first and foremost, and so I have 3 examples of applications that kind of explore the different trade-off space among integrating circuits and zkVMs. And I'll kind of explain where the boundaries lie in the space of trade-offs. And then finally, after that, in a 4th section, we're going to talk about how do you actually implement integration using both circuits and zkVMs in the same application. So the first one I want to talk about is parsing HTML and PDFs in a zero-knowledge context. So this comes into play when we think about proofs over TLS data exchange and other kind of similar things. This is a really powerful use case for identity, for bridging Web2 data into the zkVM, into the blockchain world more generally. And projects like TLS Notary, Deco, zkPass, Pado, they all provide interactive proofs of TLS data exchange to a public key, and also assuming the notary trust. I'll get back to that in a second. Proofs on the contents of that data, though, really require you to do HTML parsing or HTTP interpretation. Basically, you have to actually open the TLS data, which basically is a wrapper over TCP over a raw data stream, and actually figure out what the contents are. And for example, like make an age check on a field from a driver's license website. For example, that involves parsing HTML. Parsing is mostly control flow. The actual logic and indexing operations are very minimal. Mostly it's ifs and branches and switches and so on and so forth. And the implementation complexity is super high. There is a long, long string of bugs, including security relevant bugs, in things like HTML parsers, PDF parsers, especially signature parsers, X509, ASN1. These are specs that you do not want to implement yourself. You want to use an implementation which has been battle tested and used in production for many years. And this is what and so in this case, I would argue that zkVMs are clearly the right choice for this application in particular. All of these two factors combined, you're actually not going to get better performance from a circuit because of that control flow, and it would actually be just an absolute nightmare to implement in a circuit. So this is like a pretty clear-cut case, and this is the most clear-cut case we're going to get today. Programs are kind of the right choice here. This is a demo of this actually being implemented. So in this case, a member of the community, Wei-Kong Chen, implemented, who works for L2 Iterative, it's a fund, use zkPass and RISC-0 to implement a demo that will retrieve a US Internal Revenue Service document over TLS, and then parse it to extract verified income data that's over a certain threshold to show that you are an accredited investor in the US, which allows you to access certain private investments. So if you're interested in looking at that, that's a live demo. All right, let's move on to another case. So we're talking about succinct on-chain governance. And one thing I want to make clear is like, at the moment, I'm not talking about private. This is all public governance, basically where every voter, every vote is public. So voting-based governance is extensively used on-chain by lots of organizations. Voting is often prohibitively expensive. That limits who can participate in voting. That limits the overall coverage of your governance system, and it ultimately could impact the governance-based security that you get from your system. A lot of voting is going off-chain now, and off-chain in ways that compromises on core security guarantees and really that kind of compromises on the vision of decentralized autonomous organizations and other on-chain governed protocols. So we really need synced on-chain. We really need synced ZK verified on-chain governance. Signature verification is the bulk of the work here. So basically, votes are signed by ECDSA signatures. You need to verify a lot of ECDSA signatures. Thousands would be ideal, maybe tens of thousands as these governance models grow and grow. There's also a lot of custom logic, though. Basically, custom logic, by that I mean the people who actually run the organization will want to have their own rules for vote weighting, voter admission, and basically thresholds by which people actually vote is actually achieved. So this is kind of an interesting combination of concerns. With this combination, you need performance on the ECDSA verify front, but you also need the ability to tune things and implement custom logic, including custom control flow on the data. This means, in my opinion, this is a case where actually we really need a marriage between zkVM programs and circuits. So in this case, you might have a ECDSA verify circuit, and you might additionally have a place for organizations to insert their own control flow logic. And so we actually, RISC-0, we implemented a demo of succinct on-chain governance. It's actually not as succinct as I would like it to be, but with a new view call library that we just released as well, we're going to make it basically essentially fully succinct using a constant amount of data to verify an arbitrary number of votes, and it does so in a way that is much cheaper. And one thing I actually want to call out that I forgot as well is even without the circuits, though, it is still cheaper to run an ECDSA verify using raw RISC-V instructions and a standard implementation than it is to do L1 computation on Ethereum. L1 Ethereum on computation is really expensive. ZK proofs are already cheaper than it, even dumb ones. All right, so I'll talk about private on-chain voting. Now, I separate this out because it has a slightly different set of concerns. So when we want to actually go beyond syncness and actually have privacy as well, you need to be running on client devices. There's really no way around this. You have to do the zero-knowledge proof on the device where the secret data lives. you can, but what you can do are, yeah, and basically the proof systems that are designed to run on client devices and run well with a seamless UX, let's think, below a second, below 500 milliseconds, but even below 200 milliseconds. Like being able to prove in less 200 milliseconds is basically exactly what you want for a really seamless UX. Where you click a button, you don't have any compromises for your users. And this is possible using custom circuits. And so basically, if you have a custom circuit and a well-tuned implementation for mobile devices, what you can do is use a proof system designed for privacy, like Zkash's Halo 2, or maybe a really nicely tuned Graf 16 prover. And then basically you use that to blind the data over which the vote is occurring. Once you have those proofs, you basically have many proofs generated by many client devices. At that point, you need to make them all succinct. And so this is a case where I believe there's a combination of custom circuits and zkVM that weights more towards the custom circuits and maybe even custom proof systems or basically proof systems that are not zkVM optimal in order to make this work really well. So this kind of basically, as we're looking at this threshold, we kind of gone from zkVM implementations to circuits, and it kind of a little more into the circuit direction, including integrating multiple proof systems. And this is our Onchain Governance demo as well, if people are interested in this. This is a blog post. We're actually going to re-release this demo as well as soon with new and improved features. All right. Let's move on to the third example, machine learning. So verified machine learning inference is a highly anticipated use case for ZK SNARKs. This is verified computations over verified inferences over public models, also verified inferences over private committed models. Verified training is also an aspirational use case, but we're not really anywhere close to doing that for relevant models yet. One of the main characteristics of machine learning is highly structured computation. These machine learning models are often described in very circuit-like structures using languages like TensorFlow and Torch, which describe things in terms of structured programs, in terms of basically essentially circuits. And they're also highly data parallel. So structured computing, highly data parallel, there's no control flow to speak of. This is kind of one signal that we're kind of in the circuit side of things. Additionally, they're very computationally intensive, and you need that high throughput. So basically, we were talking about, like, so you have these, we want bigger and bigger models, as LLMs have shown, the bigger the better. And so you really want to maximize for every single ounce of performance you can get in order to actually get a usable model that produces good inferences. So in this case, machine learning is mostly a circuit problem. In fact, you want tailored circuits and even tailored proof systems like PADO or zkL that basically really optimize for this structured computation machine learning use case. So as we've kind of gone to the spectrum, this is kind of the fully circuit and tailored proof system side of things. However, I do think there's still a place for zkVMs in this model too, in particular in input pre-processing and output post-processing. If you have an image and you want to turn it into a format, you want to take your WebP image and turn it into a PNG or whatever format your model actually ingests, then then a zkVM will be a really good way to do that in a flexible way. Additionally, when you have the output, you want to integrate that with more application logic, then a zkVM will again be a good place to do that. So basically, this kind of like if you look at like this structure, the big bulk of the computation is going to be in a tailored circuit, tailored proof system model, and then on either end, you might have zkVM programs to help out. So one thing I might make clear is basically it's not a question of circuits or programs. It's a question of circuits and programs. We're gonna use both. We want them both to be integrated together seamlessly. Applications are going to be written in this kind of modular way, in this combined way with multiple representations. And this is what we see in the real world, like with traditional computers, FPGAs, GPUs, etc., coprocessors. All right, So now we talk about some examples. Let's talk about how you actually might implement this kind of this composition between circuits and programs. So the first and most kind of obvious approach is direct integration. So you basically build your base ISA, so RISC-V, MIPS, whatever you want to be, EVM, and then you also add instructions for, let's say, SHA-2 or non-native field multiplication or K26 add, and those basically become extra instructions that live inside of your ISA. No extra proofs are needed, no I/O overhead. It's all kind of tightly integrated. The downside to this is that basically you're adding complexity directly to your zkVM, and every time you add a new instruction or a new accelerator, you change the definition of the zkVM itself and the definition of the verifier as a result. So what you do is you have two effects from that. One, you break composition. You want provers using one kind of combination of instructions will not interoperate with provers who are using a different, or really verifiers who are using one set of instructions will not interoperate with ones who are verifiers using with a different set of instructions. They won't know that each other are using the same base ISA, for instance. You also have this combinatorial blow-up in the number of instructions people might want. So some people might want SHA-2 and non-native field multiplication. Some people want SHA-2 and K26. Some people want Ketchak and K26. Basically, you have this combinatorial blow-up in terms of the things that you might do. You can support them all. However, if you try to support them all, basically you have to have every single one of those constraint sets in your verifier definition or some other way of doing this. And it adds complexity either to the verifier, to the prover. You have the kind of this you have to put this complexity somewhere between the prover or the verifier or somewhere in the system. And people always make a kind of trade-off somewhere to put that. But you end up with this complexity baked into the zkVM itself. Also works only with a single proof system. So we're talking about these applications with tailored proof systems, multi-proof systems. You are hard-pressed to do that. And in this model, this is kind of dumb and obvious. We have a prover who sends a single proof to a verifier. All right. So in this model, basically, you can use your public I/O on your circuit to actually commit to the public signals on like a bus or on a message passing scheme between the zkVM and any co-processing circuits. So in this case, the zkVM basically has a view of what the message is sent, the message is received to and from that coprocessor. And the coprocessor also has the exact same view. And basically, they both either put that transcript fully into the public signals, or they hash it first and then put in the public signals. This is really nice because now you get this composability property where you have the base zkVM and you have the coprocessor, and the zkVM programs can call coprocessors that are not previously registered or even known to third parties. So basically, between two folks using the same zkVM, verifiers can interoperate and use the same verifier code and same verifier smart contract to verify proofs that might actually incorporate different combinations of coprocessors. When you actually want to be able to prove here, you'll prove all these things separately. So you'll prove the coprocessor, you'll prove the zkVM all separately, multiple proofs. Then you'll use recursion, like I mentioned before. It's actually not that expensive to produce a single proof and send that proof to the verifier. Two of the things that come up that you need that are a bit of a downside here. Well, yeah, they're a bit of a downside here. Is one, you need a commitment to the circuit itself, which some circuits, for example, like error representations in particular, don't really have a well-defined commitment key, or at least not a succinct one. You also need to possibly implement a hash function on both sides. So both your K26 add circuit might need a hashing function, which it might not previously need, which adds a bit of slowdown to the accelerator side of things. And this is where another approach comes in as well. This one has its own trade-offs, though. There's the idea of a shared memory argument. So if you have your memory argument and you need a special memory argument that doesn't need sorting, for instance, first of all, but you can commit to both witnesses ahead of time, the zkVM and the coprocessor, hash them both, or basically send them both to the verifier, and receive a single challenge that is over both witnesses at once, and use that shared witness to actually run the memory argument. Using this, you can actually have a partial transcript on each side. Basically, you have this interleaving of like read and write operations, where this one's the coprocessor and this one is the zkVM, and together they form a full transcript. At the end of each execution, you'll commit to an unresolved memory state, where basically you actually don't know if the memory argument is valid or not yet. But in the presence of both, when you give both receipts to the verifier, possibly a recursive verifier, then basically they can then check those two commits in each other. First of all, adding them together and confirming that those two accumulators result in 0, and you basically resolve the individually incomplete memory arguments. This has a trade-off of requiring reanalysis of the proof system, simultaneous production of both proofs, and which makes it more complicated to split across multiple machines. And you also will be difficult to integrate across multiple proof systems. But you get the same advantages as the other model before, and you get a very cheap I/O mechanism between the two, the coprocessor and the main zkVM. So quickly, key takeaways. Optimizing systems more than just performance. You need to consider security. You need to consider complexity, which means security as well. Maintainability, developer experience, user experience. The best combination of circuits and programs is going to be application specific. Data-dependent control flow is one thing to look for. That's like zkVM favoring. Usage of cryptography favors circuits. Client-side proving favors circuits as well. We have new approaches in composition between different proof systems that makes it much more attractive and tractable to actually do these kind of integrated circuits and zkVMs. And one thing I also want to emphasize as well here is that the best approach, which is I think is something I'm really excited about with zkVMs, is you can implement first and then optimize your program after measuring what it does on performance time. I mentioned before, for example, like signatures. You just import a dumb library, run it in a RISC-V, run it in MIPS, whatever your native instruction set is. Just run a verifier, see if it works out, and then check the performance. Don't assume it's going to be bad, or too bad at least. And I thank everybody for coming to talk. I'm Victor. These are my handles and my email. Yeah, questions?
I'll let you catch your breath. If there are any questions, please raise your hands, and someone will bring you a microphone. So yeah, just here. Okay, back to you.
Hi. If I get it right, your way to make the coprocessor and the main processor communicate is through I/O. So they commit to a shared sequence of events, and then you check that they match. Mm-hmm. Is this just a general way of doing linking, or is it just limited to coprocessors?
It's definitely more of a general. It's definitely a general approach. I mean, it's used pretty extensively both within circuits and like between circuits. Like, I guess the idea of going between circuits is kind of new with kind of the newest recursion schemes and folding schemes. For example, like ProStar is a folding scheme that can do like different distinct circuits. But I'd say that overall the approach is fairly general and I mean shared across a lot of the engineering space, not just in this space either. Transcript hashing in TLS, for example, is a kind of a similar idea. Mm-hmm.
Anyone else? Don't be shy. We're here for that. Any other questions? Oh, yeah, okay.
So related to that last question, could you elaborate a little bit on why you need to have a commitment to the circuit for linking?
Oh, yeah, totally. This just has to do with like, so when you actually want to, so I mentioned before this idea that you can actually have third-party developed coprocessors that are not part of the verifier definition broadly. The way you get that is basically the verifier and also the program itself are both part of like the trusted code base. And so what you can do is you can actually, basically you can have the program actually specify an ID, for example, a hash of some circuit definition that will bind what coprocessor can actually resolve a given request for computation. So basically what you do is you basically need an ID of some sort that succinctly identifies, for example, the ECDSA verify coprocessor. And then basically you commit in the public I/O or the shared memory argument, you commit to that ID and then you commit to your I/O. And basically when you push that into the receipt, the verifier, which could be a recursive verifier again, basically checks that the secondary receipt, the auxiliary receipt for the coprocessor, actually is a receipt of the circuit that was specified by the program's output, and also has the same I/O commitment. So basically, the reason you need a commitment or it benefits greatly from a commitment to the circuit that is succinct, is that basically that way your zkVM program can call out to these coprocessors without pre-registration at the general verifier level.
That makes sense. Thanks.
Mm-hmm. Yeah.
For integration, are there any projects you could point to or frameworks that where you like how the integration was done?
So all the projects I'm aware of currently are in the add instructions to the zkVM model, and they do it in different ways. Like Protostar is different than Valida, and SP1 is different than RISC-0, but they all kind of still fall in that bucket. And the latter two approaches are kind of new exploration. This is what I've been thinking about very recently, and what we're developing for RISC-0 right now.
Okay, thank you.
But if you see one that implements this, I'd be very interested. I may have missed it.
So for the shared memory argument approach that you mentioned, is that shared memory also impacting the memory of the zkVM as well? Mm-hmm. It's the same memory space, right? Or is it like a specific memory used only for this message passing between the VM and the coprocessors? You
can do either. I think that basically the idea of having it be a shared memory space is somewhat attractive to me. It's kind of similar to DMA on PCI cards, mm-hmm. for instance. However, there's also obviously advantages to having distinct memory spaces and memory regions that the coprocessor has control over this memory region and the zkVM over this memory region. So both models have trade-offs to them.
Yeah.
Yeah, but both are possible.
Yeah, makes sense. Thank you.
Mm-hmm.
And if we don't have any more questions, now it's time for the break. Thank you, Victor.